So my name is Mary Sheeran, some of you know me, and I have, over my entire career, thought hard about higher order functions for describing both circuits and programs. And this paper is about some further efforts in that direction. Now, Satnam already introduced you this morning to some of the higher order functions that I have loved. So for example, the function 2 will take a function f and apply it to the first and the second half of its inputs. And interleave will apply the function f to the odd numbered indices and the even numbered indices of the input. Next slide. So we can, if we think of the arrays that are coming in and out in actually column major order, then this is one way to represent that, you know, this gray part is the first function, and this white part is the second function. And for interleave, it looks like that. It applies one of the functions to the odd indices, and one of the functions to the even indices. Next slide. And I have investigated the properties of these higher order functions and wanted to rely on them in various ways. So for example, this picture gives you some motivation, at least, for the assertion that 2 of interleave of f is the same thing as interleave of 2 of f. You can kind of cut it that way or cut it that way. And that's a kind of nice, you know, property of these higher order functions. Next slide. But then it turns out that after 2 and ilv, my next favorite combinator looks like this, right? So, and I called this one Q. And I dreamt it up because somebody had designed a beautiful sorting network using this higher order function without knowing they were using higher order functions. And so the nice pictures for thinking about the properties of these higher order functions fall apart already now. Okay. So then the next question is, well, what should we do instead of vague pictures? Well, most people go now at this point for, you know, dependent types and category theory and stuff. And you might expect me to do that too. And I might even have other papers that do that. But what I decided to do here was to think about these higher order functions in terms of a particular set of permutations, and to think of those permutations, the indices into arrays, as binary numbers, and to think of the permutations as operations on those vectors of bits expressed using matrix multiplication, vector matrix multiplication, and so on. So what I'm saying here in this paper is actually a very nice way to start for reasoning about these kind of higher order functions is plain old linear algebra. It's quite interesting that I would dare to say that, okay? Now, the plain old linear algebra helps me to understand what is the nice set of combinators, what are their properties. But I think the key point in this paper that Mathis will tell you all about is that using, you know, the mathematics of linear algebra also allowed him to get speed. You know, we want to run these programs fast on GPUs, and Mathis, when implementing these permutations, was able to do some beautiful reasoning in terms of linear algebra in order to understand how to better implement those permutations. So I think that's the kind of message of the paper. So my professorial view is linear algebra is a good thing, and Mathis will show you the details of why I think that is so. And at this point, I'll hand over to Mathis to continue the talk.
Thank you, Mary. So my name is Mathis, and I'm a master's student from Paris. So I'll go on, and first, as Mary said, we'll be trying to make things run fast on GPUs. So I'll start with a bit of background on GPUs, but going fairly quickly. So the basic on GPUs, I'm sure many of you know, is that GPUs follow a single instruction multiple threads design, which means that many threads execute the same code on different data. And these threads are identified by a thread identifier, which is simply a number. These threads are organized into a hierarchy. So the top-level synchronization unit is a kernel, which is hundreds of thousands of threads, which all execute the same code. Then these kernels are divided into thread blocks, up to 1,000 threads, and this is where memory and execution synchronization can happen. And finally, thread blocks are divided into warps, which are 32 threads, and these threads execute instructions in lockstep, meaning every instruction at the same time. Then the other side of the coin is the memory hierarchy. So the big chunk of memory in a GPU is the global memory, several gigabytes, which has very large bandwidth, larger than CPU RAM, but only if it is accessed properly. More on this later. And this is where the CPU writes the inputs and reads the outputs of each kernel. Then we have shared memory, which is a couple of kilobytes in size, and shared by all threads in a block, and functions as a user-managed cache. So I'll give examples of this later. And finally, each thread has a couple of registers, which are a few bytes of memory, very fast, but very small. So then the main performance consideration that we'll talk about today is memory coalescing. On GPUs, the global memory is divided into contiguous segments of 32 to 120 bytes. And reads and writes from individual threads transfer a whole segment at a time. But the advantage is that if several threads in a single warp access the same memory segment, then these memory transactions are coalesced, meaning fused, into one transaction. So for instance, if a warp reads memory at addresses 0, 1, 2 through 31, only one memory transaction is required. Whereas if a warp reads the addresses 0, 16, 32, 16 memory transactions are required. So the second example will be much slower than the first. Then I move on to an example, which is kind of the first permutation we'll speak about. It's matrix transposition. So the issue we want to solve here is we have a matrix M of size n times n, so a square matrix. And to simplify, we'll assume the size of the matrix is a power of 2. We want to accomplish transposition. So we want to move the element at position ij to the position ji. And we'll assume M is stored in row major order in both the input and the output. So in pseudocode, we have a very simple kernel. So this is the code that every thread executes. We launch one thread for each element of the input matrix. And so each thread computes indices I and j into the matrix, and then simply reads an element and writes it at the corresponding place in the output. So this is all good, but how is the performance? So I just told you about memory coalescing. So we can look at how each warp accesses the matrix. So in the input matrix, here I grade a region in the matrix. The gray region is what is accessed by a single thread block. And then it's divided into 4 regions, which are the regions accessed by individual warps. So here we can see in the input, each warp reads part of a row of the matrix. And since the matrix is stored in row major order, this will be fully coalesced. But when we write in the output, now each warp writes to the matrix column-wise. And this doesn't agree with the way the matrix is stored in memory. So now we get an uncoalesced access. So the performance of writing to the output will be very poor. Now, the way we solve this is by using something called a tiled kernel. So now we will divide the input matrix into tiles, square tiles of size 32 times 32. And then each thread block will process a single tile and will read the tile to shared memory. Now we have to make sure also to explicitly synchronize threads because we are using shared memory so that when we synchronize, they all have the same view of shared memory. And then we write the tile back to global memory. So this is the kernel, again in pseudocode. So we have the tile variable here, which is a piece of shared memory that each thread block has. And then each thread will compute the index of its tile, which is block I and block j. This is the index of the start of its tile. And I and j, which are the indices inside the tile. And then reading the tile is as before, except now the indices are in two parts, the block and inside the tile. We synchronize. And now the trick is when we write in the output. So notice that when we use the variable tile for the second time, now we swapped I and j. So now I is in the row position and j is in the column position. And same thing, we also swapped when writing in the output. So now what this does, if we look at the picture in terms of shaded matrices, we can see that, so first of all, the grade subregion is now a square. So this is the tile. Each thread block reads and writes a single tile. But now both when reading the input and writing the output, each warp writes, processes a single row of the matrix. So now both the input and the output are fully coalesced. And if we try to run the true versions and check the performance, we get results like this. So the tile transpose is more than twice as fast as a naive transpose. And for reference, just simply copying an array of the same size is barely faster than the tile transpose. So the tile transpose is basically as fast as an array copy. So this brings us to the kind of key idea of this paper, is to think about similar permutations to transposition, because transposition is actually just moving data around in an array. So there are plenty of similar permutations, which are related to the combinators that Mary told you about in the introduction. There are plenty of similar permutations that, using a similar approach, we can implement very efficiently on GPUs. So the key idea here is to view indices into arrays of size true to the n as binary vectors of length n. And then we want to study permutations, where the mapping between a source index x and a target index y is given by a linear formula. So this is where linear algebra comes in. So here, A is a matrix, is a square binary matrix. C is a vector, a complement vector. And here, both in the matrix multiplication and the addition, we do all arithmetic modulo 2. So if we expand everything, we get this. So the ith bit of the target index y is given by this formula, matrix multiplication. And in fact, as I'll show very shortly, many interesting permutations on arrays can be described by a formula like this one. So I told you about transposition already. So transposing, for instance, a matrix of size 4 times 4 can be given by this formula. So we need to think about how to map an input index x to an output index y. Since we're transposing a square matrix, we simply take the first 2 bits of x and the last 2 bits of x and swap them. So if we write this using explicit indices, we get this formula. And we can check that it's indeed a matrix multiplication plus a complement vector. And the complement vector happens to be 0 here. So just an example to make sure we understand what's happening here. If we have the index 6 into the array, which is in binary 0, 1, 1, 0, this is mapped to index 1, 0, 0, 1, which is 9, because we simply swap the first 2 bits and the last 2 bits. Another interesting example is bit reversal. So in bit reversal, the mapping between a source index and a target index is given by reversing all the bits. So this is useful, for instance, when you want to implement a fast Fourier transform. So the index formula is simple enough, and this is indeed also a matrix multiplication plus a complement. And again, the index 6 is mapped to itself. Simply reverse all the bits. And a final example that's also quite interesting is array reversal. So when you have an array that has a size to the power of 2, you can reverse it simply by flipping all the bits of an input index x. So remember, we're doing all arithmetic modulo 2 here. So flipping the bit xi is the same as adding 1 to it. And this is indeed also a matrix formula. And now we use the complement vector, which is all ones. And index 6 is mapped to the index where you flip every bit. So this is 9. So now I'm going to give a name to a few of these permutations. So first, in the case where the matrix A is a permutation matrix, so what I call a permutation matrix is a matrix that has exactly one non-zero entry in every row and every column, so a pretty strict condition. So it's a very sparse matrix. And in this case, the matrix A simply shuffles the bits of the input x. I call this kind of permutation a BPC permutation, bit permute complement. And in general, I call it a BMMC permutation. So in fact, the 3 examples I gave, transposition, bit reversing, array reversal, are all BPC permutations. And to find BMMC permutations, because these are also interesting, I'll have to go back to the combinators Mary was talking about. So I'll talk a bit about the combinator called POM, which is a generalization of the combinators true, interleave, and that Mary told you about. So the POM combinator takes as input a binary mask with n bits, a function f, which maps arrays to arrays, and an array x's. So it partitions the array x's of size 2 to the n in 2 subarrays, according to the mask. It applies f to each subarray, and it stitches the resulting arrays back together. And then the mask is really what specifies how the function behaves. So for certain masks, we are going to obtain the true combinator. For other masks, we are going to obtain the interleave combinator. And so the way this works is that the element at index I in the array x's is assigned to the first or second subarray according to the dot product with the mask, modulo 2 again. So a couple examples. Here I have an array of size 8, and I'm showing how the 2 subarrays, how it's split into subarrays for different masks. So with a mask of 1, we obtain the interleave combinator. So the even and the odds elements are separated. On the right side, with a mask of 8, so in binary 1, 0, 0, we obtain the combinator 2, so the first half of the array and the second half of the array. And of course, there are many other masks, some interesting, some less interesting. For instance, the mask 3, in binary 0, 1, 1, we get this partition. Now, the link with BMMC permutations is in fact that one way to implement the POM combinator is to first permute the array x's such that the first subarray goes in the first half, the second subarray in the second half, and then simply apply the function f to each half. So written with a formula, this is how it works. So for any mask M, we can find a matrix A such that applying POM can be decomposed as permuting the array, applying f to each half. So remember, the mask 2 to the n minus 1 simply applies f to the first half and the second half, and then permuting in the other way. And the magical thing here is that the permutation here is indeed always a BMMC permutation. And I'm going to show very shortly how to implement these efficiently. So quick example, if we take, I took an arbitrary mask, here the mask equal to 3, we get this BMMC. And you can check that, in fact, this is not a permutation matrix, if you look at the last row. So BMMC is also very interesting. So for those of you familiar with the Futak programming language and compiler, this is similar to an optimization that the Futak compiler performs. So in Futak, when you have multi-dimensional arrays, they are automatically transposed by the compiler to enable memory coalescing. So for instance, if you have a kernel where a matrix is accessed column-wise, so here I and j are the thread indices, the Futak compiler will first transpose the matrix using a tiled kernel which is fully coalesced, and then the kernel can access the transposed matrix column-wise. Well, the trick I just showed you to implement the POM combinator is very similar, because in fact BMMC permutations are just a generalization, or one generalization of transpositions. So if we access an array in some way using the POM combinator with some arbitrary mask, this is the code that we can generate. So we insert BMMC permutations, which should be very fast as array copies, and then we get a very easy POM combinator in the middle. So now I'll give a bit of details into regarding how to implement these permutations, but you can find more details in the paper. So we'll try to generalize the tiling kernel, the tiled transpose kernel that I showed you in the introduction. So we'll start with BPC permutations, because these are easier to think about. So we consider a BPC permutation, where P is you can either think of it as the permutation matrix, or simply the permutation corresponds to the matrix. And we choose a tile size, because we're going to use tiles true to the n tile times true to the n tile, typically 32 times 32. And then defining tiles is a bit harder, because as input we don't have a matrix, we have an array, an arbitrary array. So what we'll do is we'll partition the bits of each input index into 3 categories. So we take an input index, and the tile column bits will be the n-tile lower bits of this index. The tile row bits are a bit more involved. These are the bits that, when we apply the permutation P to the index, to shuffle the bits of the index, the tile row bits are those that are mapped to the lower bits. So when we apply P to the bit index, so P just shuffles the positions of the bit, we get something, we get a low bit. These are the tile row bits. And then the thread block bits are all the other bits. And so this is a bit simplifying. Things can get a bit more nasty, and tiles can get rectangular, for instance. But I won't speak about this in the presentation. So a couple of examples. For instance, for bit reverse, this is how we split the bits of an input index. So the tile column bits are the lower bits, and the tile row bits are the n-tile upper bits, because these are the bits that, when we reverse the bits, the tile row bits are mapped to the tile column bits. For transposition, this is how we split the bits. The tile column bits are, as always, the lower bits, and now the tile row bits are the first bits of the second half. And as always, if we do the transposition on the index, so we swap the first and the second half, the tile row bits are mapped to the tile column bits. And now the way we define a tile is simply just fix the thread block bits and just varying the tile column bits and row bits. So varying the yellow bits here gives a tile. And last, I'll define a bit of notation to simplify manipulating indices. So we want to create indices using a thread block identifier and tile coordinates. I'll call this stitch. And then stitch tile is the same as stitch, but we use only tile coordinates. So we stitch. So we imagine we have a blank thread block number. We use the stitch function and we remove the thread block bits. We delete them. So this is how it worked for transpose. So here I wrote the least significant bit is to the right, as usual when you write binary numbers. So here stitching the tile column bits go to the least significant bits. The thread block bits are split into two, and the tile row bits go to the left. And the stitched tile is exactly the same as above, but you remove the white bits, which are the thread block bits. So then I'm ready to show you the pseudocode for the BPC kernel. And as before, we'll launch one thread block per tile, square tiles, and this is the code. It still fits into one slide. We'll have a tile in shared memory, a square tile, and then each thread will compute three variables. So block is the index of the thread block, warp is the index of the warp this thread is in, and thread is the index of the thread within its warp. So thread varies from 0 to 31, and warp also varies from 0 to 31. So the first step is to read the tile. So this is pretty straightforward. We just need to, so we have three variables. We'll use thread as the column variable and warp as the row variable, and thread block will be the remaining bits. So we just have to stitch everything and make sure everything matches up when we stitch. So we read the tile, we synchronize, and then the tricky part is when we write out the tile. So reading from the tile in shared memory is simple enough, except this time we reversed the role of warp and thread. So now thread is to the right and warp to the left. And when we write to the output, we have to, so first we stitch, and then we apply the permutation P to the bits, and we XOR with C. So now we can try to think about why this is coalesced. So when reading, it's simple enough, because remember that when stitching, the thread variable will become the lower bits of the input index. So this means that each warp will read 32 contiguous values in the input array. This will be coalesced. But then when writing out the tile, we can see actually that the bits of thread are also the lower bits of the output index. And this is because of the way we stitch, the stitch function works, is that when we apply the permutation P to the stitched index, the bits of thread will become the lower bits. That's why we did this whole construction of stitching and everything. And so each thread will also read 32 contiguous elements. Maybe not in increasing order, but 32 contiguous elements. So the output will also be coalesced. So this was tiling for BPC permutations. And now we'd like to generalize to arbitrary BMMC permutations. And so we can think about what we would need for tiling to work. And so the answer is that for an arbitrary BMMC, we need to find n-tile bits such that varying these bits only in the input index gives contiguous elements in the output indices. So varies only the lower bits of the output index. And so this brings us to tiled BMMC matrices, which are special BMMC matrices defined using quite a technical condition. But shortly, these are exactly the BMMC matrices for which tiling works. So I'll just show the picture here. We need to be able to find some columns in the matrix such that the grade submatrix here is invertible and the dashed submatrix is equal to 0. And the columns don't have to be contiguous necessarily. They can be all over the place. So example, and these tiled BMMCs, we can implement them using a very similar approach to BPC matrices. So now examples of tiled BMMCs that are very useful are upper triangular matrices. So in these matrices, the white region is completely 0, and the gray region can be arbitrary. So any upper triangular matrix of this form is, in fact, a tiled BMMC matrix and can be implemented very efficiently. Other interesting tiled BMMC matrices are, of course, BPC matrices, because tiled BMMCs just a generalization in some sense of BPC matrices. And then these tiled BMMC matrices that can be implemented very efficiently can very easily give us an implementation of arbitrary BMMC matrices. So using the lower upper decomposition, we can factorize the matrix of a BMMC in this form. We can factorize A as ULP, where U is an upper triangular matrix, L is a lower triangular matrix, and P is a permutation matrix. So from the previous slide, we know that U being an upper triangular matrix and P being a permutation matrix, U and P can be implemented very efficiently using the tiled kernel, but L we don't know how to do. This is a lower triangular matrix. So here comes a very neat trick. We can use a matrix R such that Rij is equal to 1 exactly when I equal to j. So it's a matrix with the ones only on the anti-diagonal. And in particular, R squared is equal to the identity. So we have this decomposition. A is equal to UR times RLP. And now UR is of this form, you can see on the right. UR is an upper triangular matrix, so is a tiled BMMC matrix. RL is also a tiled BMMC matrix. And in fact, it turns that RLP is also tiled. So we can decompose any BMMC matrix as a product of two tiled BMMC matrices. So this gives us a very simple way to implement the permutation corresponding to A. First permute with RLP, and then permute with UR. Now I'll speak a bit about the performance of these kernels. So here I have quite a bit of columns because in the paper we detail a couple additional optimizations, but here we'll focus on the true columns to the left. So the naive version compared to the tiled version, we can see that on average for BPCs, BPC permutations, we already get a pretty nice speed up. But in fact, some BPC permutations, for instance, bit reverse, are much slower than the average when implemented naively. But even those are very fast when using the tiled kernel. And for BMMC permutations, we also get a very big speed up. And BMMC permutations are, of course, roughly twice as slow as BPC permutations, because for BMMCs we have two kernels, and for BPCs we have only one kernel. And for reference, the time to copy an array of this size is around 9.5 milliseconds. So the BPC kernel is almost optimal, almost as fast as an array copy. But then we can look at the impact of the input size. And in fact, we have a greater speed up the larger the array is. So for big arrays, we have huge speed ups, but for smaller arrays, we have less of a speed up. So lastly, I'd like to finish with comparing to a paper that was written a few years ago. So the paper is Affine permutation on the CUDA-enabled GPU, which deals with a very similar question as we are dealing with here, implementing permutations on GPUs. And what this paper sets out to do is to implement arbitrary permutations. So nothing about BMMCs, arbitrary permutations on the GPU, and they managed to do it in a fully coalesced way without any bank conflicts or such. But the reason why this paper didn't end this issue is that they are quite a bit slower than what we can do here for the restricted class of permutations we are considering. In particular, they use at least 5 kernels, depending on the specific permutation, whereas we use only 1 kernel for BPC permutations and 2 kernels for BMMC permutations. and they have some issues that we don't have. Namely, they are limited by shared memory size, meaning that they can only handle arrays of size 2 to the 24, whereas we don't have any limit. But we have other limitations. So, as a summary, the main contribution of that we made in this paper is to show how to implement BPC and BMMC permutations almost as fast as copying an array. We also conducted initial work showing how to implement some array combinators such as POM, chew, and interleave using BMMC permutations. The main limitations that we couldn't solve are that this approach only works for arrays whose size is a power of 2. And the permutation matrix needs to be known before generating the CUDA kernel. So we are working in an offline setting. And a line of future work we'd like to explore is implementing these BMMC permutations and related combinators in the Futark compiler. Thank you. Should I stop sharing my screen?
Great. Thank you, Mathis, and thank you, Mary, for the talk. Do we have some questions?
Do you have any ideas for how to adjust the Futark compiler to insert those permutations where they're needed so the user doesn't have to?
Sorry, can you repeat? I'm afraid I can't put the volume very high on my end.
I'll try to speak more to the bike. My name is Alexei. I'm curious, do you have ideas for how to get the Futark compiler to read sort of arbitrarily written user code and figure out what permutation is needed? Or are the users still going to have to explicitly insert them, like it does with transpositions now?
Oh, so when writing Futark code, the way these transpositions would arise would be, of course, either you could specify them by hand if you want, but the main use case would be to implement combinators such as the POM combinator. And in the paper, we have examples of how the POM combinator and related combinators can be useful to implement programs, such as sorting networks and such. So the programmer would write using the POM combinator, and then the compiler would transform the POM combinator into BMMCs and such. Does this answer your question?
Yes.
Just a question about the limitation on the power of 2. What would be the natural way? Are there good natural ways to lift that limitation, padding and stuff? Or how do you think that can work out?
So I believe we talked about this last time we met, and I don't think I've had any significant progress on this since. So what you suggested, if I recognize your voice correctly, what you suggested is that we could treat this as kind of we do with stencil operations. So when doing image manipulation, where the user could specify kind of some border conditions, so like wrap around the indexing or mirror the indexing on the end of the array, and then have the user choose like this. And then we'd have to implement the separate modes. So I'd have to check which kind of wrapping operations can be performed fast and which are not fast. This could be a direction.
Hi. Do you have any insight on how this scale to multidimensional situations, basically? Either simple permutation or just tiling multidimensional operation.
So no, we haven't explored how this would work in a multi-dimensional setting yet. I believe Mary has some plans on doing this later on, so maybe she can give a better answer. But no, I personally haven't thought about this yet.
read it. Good. We have an online question from Edwin. He asks, can you give some examples of algorithms that you would expect to benefit from BPC or BMMC optimization? For example, maybe neural network training or inference.
Okay, so that's always the question, finding good examples. So in the paper, we go into a little bit of details about sorting networks. So that's because Mary has always been very interested into sorting networks, and running sorting networks on GPUs is kind of one of the algorithms that can benefit from this. Another example, of course, is the fast Fourier transform. So when you implement a fast Fourier transform, most of the implementations have a step where they perform a bit reverse permutation, and a bit reverse permutation is exactly a BPC permutation.
Yeah, thank you. That's very exciting. I was wondering if you look at a index on a bit level, and then you do the manipulation of the individual bits. Alternatively, you could look at it as being a higher dimensional matrix, right? So if you say you have like 32 elements, you can see it as a 2 by 2 by 2 by 2 matrix, and then you would get the blocking by means of the same mechanism, kind of. And the question is the kind of. Have you thought about this, how these things relate to each other? Because that can give you, you can express blocking through the shape as well. And the question is that the same, or is your calculus more powerful, or how do the two relate? Have you ever thought about that?
No, in fact, I haven't thought about it, but it seems like a very interesting idea to me, to think of the indices this way. So, no, I don't have anything to say about it, but I definitely have to think about it. Thank you.
Thank you.
Yeah.
Great, thank you so much. Let's thank Mathis and Mary again.